Alright, the last thing we're going to look at in chapter 3, so 3.3, is a second type of scale that uses logarithm base 10 and exponential base 10. So similar in a way to how the earthquake scale is. Alright, so decibels. Whenever you're talking about sound that the human brain can hear, alright, that's measured sound that's measured by the human brain. Right, the intensity of it is called decibels, right? They give you decibels when you hear the intensity of certain sounds. And so we're going to look at the decibel scale. It is a 10 scale. So decibels is 10 times log of the relative intensity of the sound. So it's a log base 10, which means when you flip it around, it's the relative intensity, which is equal to 10 raised to, and the reason why there's the 0.1 there is because there was the 10 out front on the log. So there's a little different, it's a little more involved in this equation than the earthquake, which was a direct inverse. This one involves, there's a 10, alright? So when we have decibels, it's 10 times the log of relative intensity. Relative intensity is 10 raised to, and you can't forget, you don't have to forget, it's on the formula sheet, so it's in the notes, and it's on the formula sheet. But that 0.1 is really easy to leave off. Again, if I'm going to do something silly, that's what I would do. Alright, so suppose that we have a radio speaker that plays music at 75 decibels. Calculate the relative intensity. Alright, so relative intensity is equal to 10 raised to 0.1 times 7.5. So it's 10 raised to the 7.5. Which comes out to 316,22776.6. Alright, so to put that in perspective, right, it seems like a really big number. But if you look at the table in the book, a regular speaking voice is at about 100 or a million. Its units is a million in relative intensity. So this is just 3 times what a normal speaking voice would be. So the speakers are about 3 times as loud as a typical normal speaking voice would be, which is about what you would expect from music. Maybe a little louder than some might want to play it at, but that's again usual or typical. I suppose you have a vacuum cleaner. Its relative intensity is 10 raised to the 8, so it's slightly bigger than that speaker system. Calculate the decibel reading. So what's an intensity of 10? So that would be 1 with 8 zeros after it. That's what that would represent. So that would be 10 million in intensity. So it would be 10 times a regular speaking voice. Well, the decibel reading is 10 times the log of the relative intensity. So 10 times the log of 10 raised to the 8, which if you type that out on the calculator, comes out to 80 decibels. Alright, 80 decibels is about what a vacuum cleaner is. Like I said, it's about 10 times more intense than a normal speaking voice. A normal speaking voice is at 1 million in intensity, and this would have been at 10 million in intensity. Alright, so just like the earthquake, we're going to kind of compare decibels here. So decibels increase in intensity for every 1 decibel on the scale. The intensity increases by 1.2. So it's not as neat and pretty as because again, there's a little more involved than just a straight log and an exponential base 10. So the intensity grows by 1.2, about. It's an approximation, but it's a pretty good approximation, 1.26. And an increase of T decibels, so this would be the change in decibels, would be 1.26 times that, or 1.26 raised to the T, right? Just like the earthquake change was 10 raised to the T. All right, so comparing, when we're comparing. So the sound of a bulldozer, suppose, is 85 decibels. The sound of a large orchestra. So the bulldozer is a little bit more intense than a vacuum cleaner, and an orchestra is a lot more intense than a vacuum cleaner. It's at 100 decibels. What's the relative intensity of the orchestra compared to the bulldozer? So we want to know the change in intensity. How much more intense is the orchestra than the bulldozer? Well, you find the change in intensity right? That's the T part. Well, you take the bigger decibels minus the smaller decibels, so you get the 100 minus the 85. So the change in intensity is 15 decibels. So how much does a 15 decibel change affect the intensity? And we're going to use this number. All right, so the increase in intensity, and I say intensity is relative intensity, is 1.26 raised to the 15, all right, which comes out to be 32. So that means the orchestra is 32 times more intense than the bulldozer. Alright, so you can feel it 30 times, you can hear it 32 times more, right? That's 32 times more intense when you have a 15 decibel change. And that's true for any 15 decimal change. So that's going from 85 to 100. But it'd be true if you're going from 20 to 35 to 45. 35. Alright, well, what if we, so the next question is asking, and this is the one, there's one like this, this is one that we like to ask, so this one typically shows up on the final exam, and it's in your homework. So suppose that we have a stereo speaker that plays music at 65 decibels. Alright, what's the relative intensity? Well, the relative intensity is 10 times 0.1, 10 raised to the 0.1 times the decibel 65. So it's 10 raised to the 6.5, and I'm just going to leave it 10 raised to the 6.5 would be the intensity of that. So again, it's a little over 3 million again. Suppose that we had two speakers, alright, so we had two speakers. What's the decibel reading would you expect? Well, a lot of times people will say, well, it'll double. But that's not true. The decibel reading doesn't double. Right, and if you think about it, kind of think about it in terms of if you have, one speaker, alright, so headphones, right? You have one speaker in your ear and one speaker out of your ear. You put both speakers into your ears. Alright, it doesn't double the intensity. Okay? The intensity is slightly more when both of them are in your ears, but not a whole lot more. The intensity is not a whole lot more. And so how that you can look at that is, well, you look at the new intensity is 2 times one of them. So it'd be 2 times 10 raised to the 6.5. That would be the new intensity. You can also use the 1.26 would work as well. The decibel reading, remember the decibel is 10 times the log of the intensity. And so I'm going to plug that in exactly. 2 times 10 to the 6.5. It again, so 10 times twice, alright, 2 times 2 speakers. The decibel reading, though, only goes to 68. So we went from a decibel reading of 65 to a decibel reading of 68. So again, it didn't double, didn't go to 130. It only went up by 3 decibels. Right? It only went up by 3 decibels. And that's typical for again, decibel reading. So let's do the second example. So again, it's a little hard to wrap your brain around, but that's the way that the 5 senses typically work, even though I have twice. So the same thing is true for taste, right? If something's really sour, all right, the intensity of the sourness, if you have one thing that's really sour and then you add 2 of them of the same sourness, it doesn't become twice as sour. It just becomes a little bit more sour. It's kind of the same thing. So if I have one speaker at a decibel of 65 and I add a second speaker of a decibel of 65, well, it becomes a little bit more, right? It becomes 68 decibels, not twice as many decibels. And again, it's the way the scale works. So let's do another example. Suppose that we have a machine that makes a sound at 80 decibels. All right, the decibels are increasing. What's the decibel change when you have 2 of the machines side by side? So we have 2 machines at a decibel of 80. It shouldn't increase by too much. It doesn't go to 160 decibels. You don't double this. It doesn't work that way. So what you do is, well, you have to figure out the intensity. All right, so the new intensity of the 2 machines. Again, of the 2 machines. And you can use either the 10 scale or the 1.26. This one I'll show you. I'll do the 1.26. So you have twice the 1.26 raised to the 80. Alright, because that's the decibels. And so the new decibel reading would be 10 times the log of 2 times 1.26 to the 80, right? 2 of those speakers. And again, it goes up, but it doesn't go up by a lot. It actually only goes up by 3, a unit of 3. Alright? Would be the same thing if you would use the base 10. 2 times 10 raised to the 80 also gives you 83. You can use either the approximate scale, the 1.26 scale, or the base 10 scale. It gives you the same answer either way if you type them in log base 10. So, check it out. Make sure I'm telling you the truth. You should always check it out. Log of 2 times 1.26 raised to the 80 comes out 83. If you round, now they are slightly off because this is an approximation, but if you round the whole number, it comes out to the same thing. Alright, because again, the 1.26 is rounded. Alright, that finishes up. So like I said, this is one that they like to ask you on the final, so it'll probably show up on your quiz, it'll show up in your homework, and more than likely it'll show up on the final exam. So do make sure you understand it, at least understand how to find it, because you will be asked to do it. Alright, we'll stop there. We're all done with Chapter 3.